Okay, let's begin. We're going to pick up with the proof in the book on sufficiency. I'm going to talk about it in a couple different ways. I'll tell you what, like, all the insight I need. I don't actually need this proof concerning experimenter 1 and experimenter 2, but I think it's interesting the way they go about proving this. They have a passage and they start telling you all these distributions are the same, and they start changing the notation on the random variable. And it's like, what's the random variable and what instance is it? And they're very specific in that notation with the random variable. The passage preceding all of that shows you equivalence between a whole bunch of distributions. And they hope that you have all that in mind, and you're nimble enough for this one line of a proof so you can substitute everything. We're going to talk about that one line of a proof. If you've read through it and read through that page in Cassell and Berger, you know exactly what I'm talking about. So this all appears on just a single page. I'll let you read through it, and I'll kind of modify this proof ever so slightly. And hopefully that makes you feel a little bit better. If it doesn't, when you get to the end of this proof, give me another moment, and I'll show you an example, a little bit more complex of an example, and I'll tell you what experimenter 2 can do. And then hopefully it all comes together. I'm not going to ask you to prove this on a midterm or a final or anything like that. I'm going to ask you to please understand and be able to demonstrate everything. So let's just talk a little bit about this distribution for a moment. So in the sufficiency principle, they say the principle is that there's some statistic out there and it preserves all the information about theta. So whether or not I get to see the whole data set or I get to see a particular statistic, T of X, which is sufficient, I have the same information about theta. That's the principle. And then they tell you the property of the sufficient statistic. So this is the property that we put into play. And the property is such that if I have some distribution, and I can think about whatever this distribution is, I know how this data was generated. So I have the model. And so again, sufficiency is a concept that requires you to have the model in hand. So you can't say a certain data set, if you just look at a data set, you can't ascertain what the sufficient statistic is until you have the model. And so what that really tells us in reality, where we only get to see the data and model isn't given, you need to store all of the data. The data itself is sufficient because it's going to give you the ability to test all of your assumptions about that model. So usually we come up with the model after we see the data. And so sufficiency is certainly something you can exploit. Minimal sufficiency is something that you can really exploit on a computer, and we'll talk about the practical aspects. I think when Fisher was thinking about all of this stuff, so he's kind of the grandfather, when we get into hypothesis testing, my opinion of Fisher's work kind of goes down. But in terms of just defining what happens with all these various statistics and all of these mathematical properties, I hold nobody in greater esteem than R.A. Fisher, because he kind of carved all this stuff out for us. Understood the importance of randomization, understood the importance of properties of statistics. So he comes up with this idea, there's a sufficient statistic, it's got all the information about the sample, and then he starts thinking about, are there other statistics out there that have no information about the parameter? And so sufficient statistics have all the information about the parameter. There's some statistics that have no information about the parameter. What are those statistics called?
Ancillary.
The ancillary stats. And so Fisher was kind of thinking, well, those belong in two wildly different spaces. And so in some sense, they should be orthogonal to each other. They're independent of each other. And it turns out that's not quite true. And there's another type of statistic out there called a complete statistic. And if your sufficient statistic is complete, then it's going to be independent of all ancillary statistics, so that they're orthogonal. I never used the completeness thing in my life, but from a mathematical perspective, that's all super interesting. It's like, when do these spaces overlap each other? We will only allude to completeness in this class. I'll tell you what it is, I'll assign one problem to you so you can see that it's hard to verify that your statistics are complete. What I'm going to guess you're going to do is you're going to go find the solution manual and go, how would I have done this if I just got handed this? And so I've never seen a statistician, you know, when somebody says, okay, I'm conditioning on the sufficient statistic and I'm going to use it, nobody has ever asked in the history of stats, is that sufficient statistic complete? So that I can see that it's independent of all ancillary stats. It doesn't happen. So really what you want is you want to be able to use sufficient statistics. And that's, from a practical standpoint, that's all you really need to do. You might want to compress that thing so that it's as lightweight as possible, so that you can compute fast using it, not store as much stuff. Okay, I said a lot of stuff. We're going to go through sufficiency, we'll go through minimal sufficiency, then we'll go through ancillarity, and I'll just allude to the completeness thing in a theorem called Bassu's theorem. So we're not going to spend any real time, substantial time on Bassu's theorem, but it says something about the orthogonality of these two spaces, given that a sufficient statistic is complete. Super mathematical concept, very abstract in my mind still, interesting, of no practical value. So, it doesn't need to have practical value to be worth doing, you know? So I think we all have stuff like that. So some of you guys like to go play video games that say have no practical value, but maybe it gives you some peace. So I like playing Rubik's Cube and playing Tetris. That's about as much as I can do. So what's the practical value of me playing Tetris? None. So it's fun. So maybe this stuff is fun to you, maybe it's not. Okay, let's get on. So I want to just talk about what this distribution is right here. And so the definition of sufficiency is going to say that the conditional distribution of x given the sufficient statistic and the parameter is independent of the parameter. It doesn't involve the parameter. So once I condition on the sufficient statistic, the parameter falls out of the equation. Let's just see that. And so this is all very intuitive to me. They go on to make a more complex statement than I'm about to make. So what is this distribution? So f of x given tx and theta, and I'm just going to write in the theta right here, although this theta is going to fall out of the equation. So if t of x is sufficient, that theta will not appear. So what is this thing? We'll just apply some basic probability theory. F of x, t of x, given theta, divided by f of x, f of tx, given theta. And if somebody wrote that down for me, I would say, yeah, I don't need any further justification. I understand how to condition on things. So I take the joint distribution and I divide by the marginal distribution. So the margin on tx. And that's what this thing is. And we learned that in probability theory or Stat 101 a long time ago.
Are these apps the same? Like,
yeah, they're not the same. This is the curse of statistics, that they're different distributions. So if you would like, you can always do this. So what I mean right here is this is going to be x given tx and theta. So that's a different thing. So I can just look at the arguments right here. So they're not the same functions.
okay.
So we use p's all the time, f's all the time, and we mean something different. So this one would be the joint distribution of tx and given theta, and this one is for tx given theta. Okay, let's look at an example and just see what these distributions are. So they're not the same, and they're probably not the same all the time I use that. They are different. And all you have to do is look at the random variable that's being plugged in there. And that's going to define everything. If you want to be more polite, you would subscript this. I usually do not do that. So in my papers, I just assume you know that the F's are different. So here's an example. We've been studying this example. We'll look at another example after we go through the proof. So then we'll do example, proof, example. So maybe the XI's are Bernoulli's, our old friend. I goes from 1 to n. And then my T of x for everything is going to be the sum of the XI's. We're already comfortable and we know that this thing is going to be the sufficient statistic in this model. So, and my distribution, I goes from 1 to n, which is T of x, is going to be distributed as a binomial probability T. So for this, right here, this is going to be f of x given p. So p is my theta in this example. This is going to be equal to product. I goes from 1 to n, p to the xi, 1 minus p to the xi. And you can simplify this. P to the sum of the xi's. I goes from 1 to n, 1 minus p, n minus sum of the xi's. So same thing that we've had for the last several lectures. And f of sum of the xi's, which is just my T of x.
Is there a 1 minus xi?
Yes. 1 minus.
What are oh no, sorry.
Say what? We know what this thing is. This is going to be n choose sum of the xi's. P to the sum of the xi's. 1 minus p, n minus sum of the xi's. Okay. So they're different distributions. These distributions, if everything is sufficient, they have the same kernels. So back to Anchor's question, are they the same disk? They are not, but if they are sufficient statistics that we're looking at, it turns out they have the same kernels. And what do I mean by the same kernels? Everything that depends on the parameter. So this function right here and this function are the same. That's the kernel of the distribution. So I'll just write this down, kernel for the xi's given p. I goes from 1 to n, and this is going to be the kernel for sum of the xi's given p. So same kernel, so the distributions are different, but in this at least setup, considering that we're working with sufficient statistics, those distributions look functionally the same in terms of their parameter space. So this is what happens. So if I'm going to compute this for my example, so this is my Bernoulli example, Bernoulli binomial. If I take the ratio of these two things, all the stuff involving p cancels out. So this is just going to look like 1 over n choose sum of the xi's. I goes from 1 to n. Does anybody recognize this distribution? What kind of distribution is this?
Uniform?
It's a uniform. So it's uniformly distributed. So it's 1 over all of these combinations that you can make, where you can't distinguish the ones and zeros, and I can flip them around. So this is a uniform distribution, where this is the number of possibilities. So it's not always going to be a uniformness thing, and we'll look at an example after we go through the proof where it's not uniform, but this is a uniform. So it's a uniform over this discrete space of vectors of ones and zeros such that everything sums up to all the sums of the ones and zeros are sum of the xi's. So, and that's what that is. So we're going to be thinking about experimenter 2 being able to sample from this distribution. And so somebody could sample from this. So to sample from this would say, give me a vector of ones and zeros such that the sum of the ones and zeros is sum of the xi's. And you could do that. And so how would you do that? You'd make a really big hat. You would have little vectors in there of ones and zeros with all the different combinations of ones and zeros such that everything's summed up to sum of the xi's. So every ticket in the hat is this long vector. And you're going to shake that hat, and you're going to reach in there and take a rabbit vector. So, and that vector is going to have all the same information about P in our context that any of the other vectors will have. So I could sample any one of them, and they'd all have the same information about P. So that's the little caveat in the proof that gets a little bit confusing. So let's just meet our two experimenters again. Experimenter 1 gets to see the data. So then experimenter 1 knows in this example what the actual true sequence of ones and zeros are that got observed. And experimenter 1 can compute the sufficient statistic. In our Bernoulli example, experimenter 1 can sum up the ones and zeros. Experimenter 2 just gets to know what the sum is. So in general, experimenter 2 only gets to see T of X. Both of them know the model. So they know the functional form of everything. Experimenter 1 gets to see this vector and compute the statistic, and experimenter 2 just gets to see the sufficient statistic, but they do know the functional form. Neither one of them knows what theta is. And they're going to both guess. And this proof is going to tell us that they're going to probably guess the same. It doesn't tell us exactly how you build your estimator, but it tells us at least the probability distributions that they're going to be working with are the same, and they have the same information about theta. So what they do with that at the end of the day, we'll need chapter 7 to help us out with. Okay, so I want to just point out what this distribution is right here. This one is exactly the same as fx given theta. If I know x, I can compute t of x. There's no stochasticity in it. All the stochasticity, all the randomness is in x. And so this thing right here is equal to that. So I can vary in t of x and there's no extra information. And so those probability distributions are governed by the randomness of x. And t of x is just along for the ride. And it gets computed without any randomness. So you give me x, I'll compute t of x, and it's a number. So there's no extra random fluctuation in there. Of course, if I don't tell you x, then I have randomness on t of x. So that's what that thing is. So this is really just the ratio of these two distributions. So this conditional distribution right here is the ratio between these two distributions. And of course, if they have the same kernels, then all the parameter will fall out. And it won't be a function of the parameter space. And that's all that says to me. So they have the same information because they have the same shapes. So let me just write this down and then we'll look at Cassell and Berger's proof on everything. So I'll just say this right here is just f of x given theta divided by f t of x given theta. And so this is equal to a constant. So constant if fx given theta and f(t) of x given theta have the same kernels. And I'm going to write that down just a little bit different shapes. I.e. the kernel is the same. So I'll say their kernels are the same. That's how I think about this. So if the distributions have the same shapes, they have the same information. The way they wiggle. And so I can figure out area under the curve relative to other parts of the curve. And those areas are going to be relative to each other. They're just off by a constant. And so in this case, the distributions are just off by this multiplicative constant. So it's just raising it up and down when I multiply by something. It doesn't change the shape of the distribution. Okay. So that's, for me, I'm ready to move on. But I still like this proof because it used to confuse me what was happening in the proof. And now I'm no longer confused. So this is the proof I think I was alluding to in review session that I looked over to my senior graduate student office mate and I said, John, help me out on all this. I don't understand this line of the proof. And he's like, it's quite obvious. A couple hours later, we understood why it was obvious. So it takes people a long time to think about things sometimes. So I'll try to give you all of that mental thought. Okay. Let's give myself some room. And let's start moving through this proof. We're going to show, get rid of this. Here's the little caveat. Experimenter 2 can generate a new vector, at least in my context of my Bernoulli example. Experimenter 2 can generate a vector of ones and zeros. So how's experimenter 2 going to do it? They're going to sample from this uniform distribution. It's going to be a little bit more complicated in my next example. We all know how to sample from that distribution because it's just dropping things into a hat and giving it a shuffle. So pretty easy conceptual mechanism. Experimenter 2 can generate a new data set we're going to call it y, and the random variable associated with it is going to be cap y. So random variable is cap y. And how are they going to generate this data set? They're going to generate from the conditional distribution that we just wrote down. They're going to generate from this distribution. Experimenter 1's random variable, I'm going to call x. So that's my random variable. So I'm going to change my notation a little bit and say this is the observation that they actually get to see. So x, in our case, is the random variable, but this is going to be the observation. So usually I'm not very careful about distinguishing between the two things, and we butcher the notation and we just kind of invoke that there's a random variable there, but we're always just plugging in the instance. So if that bothers you a lot and you want to think about it a lot, bravo to your mathematical stubbornness. You know, it's kind of what it is. I'm not stubborn. I like to know what exactly is this that they're saying. So, okay, let's just start marching through this. What we're going to show that fx given theta is equal to fy given theta. And I've kind of butchered the notation and suppressed at least what the instances are in here. But we're going to show that these two random variables are the same. So that experimenter 1 and experimenter 2 can see. Experimenter 1 gets to see the data, experimenter 2 is going to generate synthetic data such that that synthetic data has the exact same information about theta. So let's just march through this. So proof. And I'll be a little bit more careful about things, and I'm going to change some of the notation that Cassell and Berger use. So they're going to start out with f of x is equal to little x given theta. So I think this is the correct way that we're supposed to write it down. This is my space that everything lives in. This is denoting that random process of going in there and fishing out a little x. So this is my observation. So I can reach into this distribution and grab one of these. So that's what experimenter 1 gets to observe. Observation. And so experimenter 1 can just take this thing, plug it into their model, and then somehow use whatever this function is a function of theta to infer theta. So if you're a maximum likelihoodist, you maybe maximize that thing. If you're Bayesian, you multiply by a prior and you come up with its distribution. If you're somebody else, you do whatever it is you do. So lots of different things you can do once you can write down this distribution. What do? I write down its likelihood. I usually penalize by a prior, and I think about it as a posterior distribution. You might do something different. We'll decide once we get into chapter 7 and talk about building estimators and what their properties are. So this is the easiest line of the proof, and we recycle this line over and over and over again. So cap x is equal to little x, and cap t of x is equal to t little x. So I can compute that thing. Here's my random variable on that, given theta. So no extra information just by computing the statistic. All the randomness is governed by x. So probably the easiest line in the proof is just this factorization. So this is going to be given t of x is equal to cap t little x and theta, and then I'll just multiply by cap t of x is equal to t little x given theta. So we're going to invoke sufficiency here that I get to cancel that out. So note that we're going to say, before we even begin this, that t of x is sufficient. So we're doing this proof in the context that t of x is sufficient. So we get to start out with that. And so it doesn't depend on theta because that's our property right there. And I could even build this distribution for you. So no theta in there. So this thing is going to be equal to fx is equal to x given t of x is equal to t little x. F tx is equal to tx given theta. Okay, so we lose the theta because it's sufficient. So I'll just write this line right here happens due to sufficiency. That's our property of the sufficient statistic. And this is where the proof gets a little bit weird. And what they write down in the book, they make this substitution real quickly. So F, and don't write this down right now. This is in your book. So I'm going to change it just ever so slightly. So they end up writing Fy is equal to X. And this is going to be conditional on T of X is equal to Tx right here. Now what they're saying, and I'm going to change this in just a second. Second part remains the same throughout this proof. This part never changes. What we just changed was this thing right here. And they have this big discussion beforehand saying experimenter 2 can draw from some distribution and create that vector X. What I don't like about it, at least conceptually, is that experimenter 2 necessarily constructs the exact same X as experimenter 1. So I'm going to change this, and I'm going to put a little Y right there. So experimenter 2 can draw from a distribution and construct a vector. In our Bernoulli example, experimenter 2 is going to come in and they're going to sample from this uniform distribution. And they're going to grab a new vector of 1s and 0s, but that vector is going to be constrained to have the same number of 1s and 0s as experimenter 1 got to see. So that vector will sum to some of the xi's. And so I'm going to just write this down, that this thing right here is Ty. They don't write that down in the book, but in the preceding paragraph, they have all of these claims that they're the same random variables. This is the same thing right here. This is going to be Ty right here. So my constraint is that this vector that experimenter 2 is going to generate is going to have the same sum as what experimenter 1 got to see. So how do they do it? Experimenter 2 goes to his hat, shakes the hat, grabs a vector. It doesn't need to have the exact same vector as experimenter 1. But what they're going to argue in all of this is that Fy is equal to Y given T of X is equal to T of Y. The reason this is confusing, or T of X is equal to T of X, is that all of these things are the same. So this is the same random variable. It's no different. So this in experimenter, or in our Bernoulli binomial distribution, this is just a distribution of the sum. And they're going to generate this vector so that that thing is equal to Ty. So this is a constrained distribution that experimenter 2 is able to sample from. The constraint is that the sufficient statistic that I compute from Y is exactly the same, which is what experimenter 1 has. We're going to see another example where this is a little bit more cumbersome. And we might not know how to do this sampling. And I'm going to end up with a punchline, do something like Metropolis. We don't need to do Metropolis to sample from a uniform distribution. You could do this if you needed to. So you could do it on a computer and you don't need your conceptual app. You know how to draw uniforms. Okay, so this thing right here is exactly the same as this. It's the same probability distribution. They're not different from each other. So the only thing in the proof that they sidestep is they don't tell you that experimenter 2 didn't generate that exact same vector. Experimenter 2 can generate a different vector, but it's going to have the same probability distribution. So what I mean when I go to this distribution right here is those vectors of 1s and 0s are all distributed exactly the same. So they're all uniformly distributed. And it doesn't matter which one I grab. And so long as the constraint is adhered to, these distributions are the same. So So, and that's the big deal right here. So I'm going to change that to y for a second, and then I'm going to add this extra thing right here that I can make that x, that the distributions are the same. And they write this in the middle of that page in Cell Inverter, that they're like, these two distributions are the same, so we can substitute them in and out for each other. And so that's that like thing that's bolded right in the middle of the page, that those distributions are the same. And so I wish that they would have just plugged in one extra line and said that this was a y right here. So I'll do it for you, and all of these constraints are matched. This is the same random variable, and this is the exact same number. So this is a number right here. In our context, it's sum of the xi's for the Bernoulli problem. So you can interchange them because they're all the same. So hopefully that kind of makes sense. So what I really want you to do is think about what experimenter does right here is they sample from the uniform distribution. I'll show you a different distribution in just a moment. And we'll talk about how that sampling can happen. So this is equal to Fy is equal to x, because they're the same distributions, but experimenter 2 really, in reality, is sampled a different vector. So given t of x, and I'll use the same notation that they use in the book, times f of tx is equal to tx, little x, given theta, and then I just roll this same line backwards. So this is going to look like f y is equal to x, tx is equal to tx, given theta is equal to f y is equal to x, given theta. Now, I don't mind if you do this right here. Oh, I am just taking that out right there. I should say something about it. That this isn't any extra information so long as I have whatever that vector is. And so they're exactly the same. So it's really just this line as we move from here to here. I did the exact same thing in reverse. So this is just backing out of the first line. And so what we have is that this thing is equal to that. So they have the same information about theta because they have the same distribution. So on this, if you'd like, we could have written this down as a y. So experimenter 1 doesn't need to see, or experimenter 2 doesn't need to see x. They need to see this vector y. So I kind of like it like this. It makes more sense to me that let's talk about experimenter 2's vector and just show that they're exactly the same. So this would be Fy is equal to y. I would have preferred it this way, but that's just my arbitrary brain being arbitrary, and I have preferences. So, but really, this little vector y that experimenter 2 generated has all the same information about theta that experimenter 1's vector has about theta. So I like it that way. So, because I can write it down just like that. And so, saying that, I could substitute in and show that these two things are exactly the same. And so it doesn't matter which one I write. And that might have been confusing to you that y is equal to x, or y is random variable. The draw that I got was x. You don't need to have x. You just need to have some vector such that the constraint is adhered to. Does that make sense? Hopefully. Chew on it for a little while. If you don't like any of that, and you're not used to thinking about random variables and what it all means, and this is a little bit new to you, and you're thinking, I'm an engineer, so I don't care. You can think about it just that the kernels of the distributions have the same shapes, so they have the same information. The shape is the information, how that thing wiggles around. So in a normal distribution where it's centered and what its diffusion looks like defines the distribution, which defines the information in that distribution. Okay, let's look at another example. And this is in the book. But I want to take it one step further and think about poor experimenter 2, what experimenter 2 needs to do if they're going to follow this procedure in the proof. A new example. Xi's are going to be normally distributed with parameters mu and sigma squared. We're going to get to see n observations. I'm going to say this is known, sigma squared, so we'll make it a little bit easy in this problem. So this is known. And we're going to try to infer theta, or mu in our case. So theta is mu. Okay, so I'm just going to write down f of x given mu, and I'm going to suppress my notation on sigma squared. So I'm just going to remind you, using this notation, that mu is the unknown parameter, and sigma squared is known, so I'm not going to even condition on it. So it's in there. It's just my choice of notation. How would I interpret this? Is a conditional probability. How might somebody else? So for instance, our colleagues here at Virginia Tech in the philosophy department, they would be up in arms if you interpreted this as a conditional probability. We'll let them have what they want, and I get what I want. So we can all have it. It's all just in our minds anyway. Okay, this thing is just I goes from 1 to n, 1 over square root 2 pi. I guess I'll write it like this. I usually duck that sigma outside of the square root. I'll put it inside. We'll get some nice cancellation. 1/2 xi's minus mu squared over sigma squared. We'll do a little bit of simplification. So this is going to look like 2 pi sigma squared to the minus n over 2 e to the minus 1/2 sum. I'll bring that product into the sum sign. Xi minus mu squared over sigma squared. So all the same thing. Let me just rewrite this a little bit differently. So this is going to look like e to the minus 1/2 sum. I goes from 1 to n. Xi's minus mu, and I'm going to add a funny form of 0. So minus x bar plus x bar. So this is 0. So I've done nothing to the equation. I'm going to add some braces right in here, just make it look a little bit different. There is a square right up here. And so what I'm going to do with that is I'm going to expand that square. So I'll just use another line, 2 pi sigma squared minus n over 2 e to the minus 1/2. I'll just make this easy. This comes up all the time. Anytime I see that squared error loss function, I add and subtract in x bar. So I know that that distribution is going to be centered around x bar. I only need to see this so many times before I can just remember that. So this is going to be xi minus x bar squared minus 2, or sorry, this is plus 2. Xi minus x bar minus mu minus x bar minus mu squared. So I've just expanded the square.
Can it be plus?
Plus. The hardest things to do.
It's all over sigma squared.
All over sigma squared. Thank you, guys. 2 pi sigma squared minus n over 2. When I slide this sum in right here, I'm not going to get any reduction right there. But if I end up looking at the sum, when I slide it in, 1 over n xi minus x bar minus mu, And I can factorize that outside. The only thing that depends on the xi's, or depends on I or the xi's themselves, so I'll put my x bar minus mu right here. This part of my sum is always the same thing. What is it? That's 0. So some of the xi's around its mean is 0. I'll just expand it. That's sum of the xi's. I goes from 1 to n minus n x bar. N x bar is sum of the xi's. So this thing is 0. So we can just get rid of it. Always true. So this is going to be e to the minus 1/2 sum of the xi's minus x bar squared. Plus, and I'll just be specific, the sum only is operating on this. Once I operate on this thing right here that's a constant, I get the n multiplier. X bar minus mu squared. So let me just write this down one more time. 2 pi sigma squared minus n over 2 e to the minus 1/2 sum of the xi's. Oh, and I did it again. Sigma squared. Sum of the xi's minus x bar squared over sigma squared times e to the minus 1/2 n x bar minus mu over sigma squared. And I can write that down a little bit differently. I can write it like that if you like. Let me just ask you a question before I continue. What do you think that's sufficient for? So just as a side question.
Mu.
Sigma squared.
It's sigma squared is the answer. And the reason why is I can't ever untangle that from sigma squared. So this statistic right here is sufficient for sigma squared because I can't get rid of it. So we'll see that in the factorization theorem. That's really what's happening. So good job, that's sigma squared. So it's the stuff that you can't untangle from it. Notice that all my mu's right here, I was able to untangle it from all of this other stuff. The distribution for my test statistic so we know this. Note f of sum of the xi's, and I could divide this by n if you want. So just kind of depends on what I want to do. But this thing is sufficient. If some of the xi's are sufficient, so is this thing. And I'm going to let this be my sufficient statistic. One-to-one functions of sufficient statistics are sufficient statistics. So given mu, we know what this distribution is. It's going to be 1 over 2 pi sigma squared over n e to the minus 1/2 x bar minus mu squared over sigma squared over n. And that whole part of everything is almost right here. So the kernel of everything is right here. And we're going to see cancellation. So I'll just write down one more line and then we'll come back next time and discuss poor experimenter 2's problem. So when I do all this, I'm going to have f of x given mu divided by f of x, or I'll say f of tx given mu. And we know what this thing is. This is going to be f of x given tx. those are the same. This is just going to be 2 pi, and there's some cancellation in here if you'd like to do it. You can do it. Over n over 2 divided by 2 pi sigma squared over n. This is to the minus 1/2. You can simplify that if you'd like. The important bit is it's constant. So, and I have cancellation between this and that last part down here. And the only thing that's remaining in there is e to the minus 1/2 x bar minus mu squared over sigma squared. And there's an n in here as well. Oh, and that's not a mu. That's xi's, to get this right. Sum of the xi's is not the n here. This is xi minus x bar. This part. So that's a distribution that doesn't depend on mu. So experimenter 2 is supposed to sample from this distribution. And experimenter 2's task isn't the easiest thing in the world. What is that distribution? Does it look familiar to you?
Chi-squared. A little bit. It's like e to the chi-squared or something.
Yeah, it kind of looks like maybe something's chi-squared, but it's not. It's a little different. So there's a constraint in this. So this kind of looks like a normal distribution. All the xi's look normally distributed and it's centered around x bar, but there's a harder constraint in there. That every time I take a sample out of this thing, and elements is those xi's have to sum exactly to x bar. So I'll just make a note. Note. Sum of the xi's over n has to be equal to x bar. So in a normal distribution, what we have is we have a mu right here, and the sum of the xi's divided by n is close to mu, but it's not exactly mu. So this kind of looks like a normal distribution, but there's a very hard constraint that everything must satisfy. So experimenter 2 has quite a task at hand being able to sample from this distribution. And so my answer to this, how experimenter 2 would do it, is they might use the Metropolis algorithm. So I'm going to come back on Monday, talk about how experimenter 2 would do this, and then I'm going to jump into minimal sufficiency. So we'll take this to the next step. And I'll outline that extra credit homework problem I've alluded to about using Metropolis. Just one more set of announcements. I'm going to give you a midterm on Friday, next Friday. I'll probably post it on Thursday morning or something like that. You'll have a week to turn it in, and there'll be the instructions. What you'll do is you'll photocopy it and send it to both me and Mohammed. So you'll have an entire week to do midterm 2. My only stipulation is you don't get to collaborate with each other on it. It'll be open book, open notes, open everything, but this is your own task. You'll send it over. I'm hoping for all 100s. Take-home test is supposed to be 100% every single time. So in my take-home test, I'll never say closed book because it's unethical.
Okay, can we Google link?
Yeah, you can touch Google. All the things that you would be tempted to do minus consulting each other, you can do. So I'm not going to put you in a situation where you can't do the thing that I know you're going to do. So anyway, I'll remind you about all that. And I will be posting 2 extra lectures after Wednesday's class. So what I'm going to probably do is run over to the conference room, knock out another 2 hours of lectures, and then you'll have something to keep you occupied during those days where I'm out of town. Bunker.
Our homework is due next Friday, but if you're out of town, how are you going to, should we just photocopy it and send it to you?
Yeah, you probably know what the answer is every single time on this. I'm always going to say you get the extension through the weekend. So I usually push you to try to do it sooner, and then if something doesn't make sense, I give you an extension. So you can already kind of mentally factor in, and I'm going to say you can turn that in Monday in class. If you want to turn it in on Friday and photocopy it, that's fine too. Awesome, you guys. Have a great weekend. We'll pick up with this one more time, talk about experimenter 2, what they need to do, and we'll show you how we can do it. So unfortunately, when they concocted this group, the process wasn't around, and this would be a really hard problem. All right. Thanks, you guys.